Hi everyone, my name is Tovio Roberts, and this is another episode of Latent Topics in Data Science. Today, we're going to explore some concepts related to image processing. And what we'll be doing is a sort of novel approach I took for creating input data for a research project a couple of years ago. And we'll be using data from one image to modify another image. So I have some images from the Kaist dataset of parallel RGB and thermal images, right? So this is the Kaist multispectral pedestrian data detection benchmark. And I'm just going to be using the images. Notice that there are these bounding boxes. These are actually stored in a separate file. And, this is a data set that you can use to train, let's say, train a neural net. But we're just going to be playing around with the images. There's this kind of convenience of having parallel images, and we can just decide what to do with that. So this data set was built from video taken with parallel cameras mounted on a car. One camera was a 3-channel RGB camera, taking the type of video we would think of as normal video, like this. And the other camera is taking thermal video, in other words, creating video from passive heat detection. So like infrared, this may actually be infrared, but depending on the type of camera, it can be an infrared camera. There's like a gradation of different cameras, right? Thermal cameras are something like infrared cameras. It just depends on the specifics of the camera. And I don't know if that information is here. It probably is. But if you want to grab this data set, it's huge. I think it's 91,000 images. You can download it from this pedestrian benchmark link, which I put in the description of this video. This is the repository we're going to be working out of, this merge RGB and thermal images. And actually, let me kind of navigate there. And let's see. And I called this merge. Oh. Okay, there it is. Okay. Let me just make this a little bit bigger in case we need it. And there we go. Drag that up a little bit. All right. So I'm working with a small subset of the case data. And since I want you to be able to sync these from GitHub, so you can play around with them. And yeah, why don't we take a look at some of these images? I think I have a directory open of those. Just track those down. Okay. So I'll just open a couple of these, and I'll open them up parallel to each other. And this one. So maybe I can just resize these a bit. The thermal image might be kind of hard to see here. But, if you take a look at these, some things might stand out to you, like the light bulbs, right? The light bulbs are warm. Humans are warm. There's underneath the engines, there's this car hood, which I think is kind of interesting. Because it kind of looks like this car is parked, but maybe it was parked recently and the hood the engine is still retaining some heat. So you get some signature from that. There are parts of buildings that are probably retaining heat from the day. And definitely people. So when I was working on this project before, we were trying to find nice ways to optimize these images as input for a fusion neural net, fusion CNN model. And, we were looking at different pre-processing and different alignment. And as you can see, really, these images are reasonably parallel. It turns out actually that they are not exactly parallel due to some offset in the camera. So you can imagine there's two cameras side by side, or maybe they're fairly far apart, maybe a foot apart. In this version of the Kaist images, the offset isn't consistent either, right? So across 91,000 images, you're placing cameras in different places on different cars. I'm sure they went for some level of consistency, but it turns out that there's some kind of offset. You can see that in the bounding boxes on some images, like there's a much more significant offset on some. I don't have examples of those, but that's not really going to affect too much what we're doing, because mostly we're just going to take some pre-processing approaches. So it would actually be challenging to create a reasonable linear transform to correct these offsets, just as a side note, because the offset is different across all these images. So as a pre-processing technique, we're not going to be doing that. That's something that would have to be fairly intelligent. It would have to involve various types of skew, and I think that would be best served by a neural net. That said, these images are reasonably parallel, and we're going to use that property to make some interesting stuff. For this project, I'm going to separate out our types of functions into 4 different Python files. I'm going to be running code in a Jupyter notebook and pulling from those 4 files. So there's an image utilities Python file, OS utilities file, a plotting file, and a merging file, which will be our heavy lifter. That's where we're going to see the interesting stuff that we're going to do. So I'll go ahead and make these files right now in the terminal. So over here, let's see, I'm going to make a directory called, let's call it merging utilities. And I'm going to make 4 files. I'm going to make image utilities, and I'm just going to call it image utils, and merging, OS utils for reading things in, and let's put our plotting functions in a separate file as well. So, what did I do? Okay, I didn't put those in the right place. So why don't I go ahead and move those into the merging utilities file. And, oh. Oh, okay, no, we're good. All right. So as you can see, we've got 4 Python files that we're working with. In this base right here, I'm going to run VS Code. And wait for that to spin up. Okay. My little intro script came up. And this is the actual place where we're going to be working. Okay. So notice in here, I've got 4 files: image utils, merging.py, OS utils, and plotting.py. All right. So I'll go ahead and start a Jupyter notebook as well. And I'll just make a second terminal instance so that I can run code in the terminal as well when I need to. And in here, I'm going to type Jupyter notebook. And that should just wait for that to spin me up a Jupyter notebook. Okay. Yeah, and sorry if I was a little late today. Like fixing some kind of environment issues on my machine. And still seems like I'm having some issues. So hopefully that won't get in the way of anything. All right, finally. Okay. So this is Jupyter Notebook opening, and I'm just going to use Jupyter Notebook to run code. And so I'm going to make a new Python 3 notebook. Hopefully these environment issues don't bog us down too much. I'm not sure about this lag. Okay. All right, so let's call this, I don't know, let's call it simple image preprocessing. And I'll go ahead and take that, and I'm going to sync that up to GitHub if you want to use these files directly. So I'm just going to do create files. And this should also be uploading the thermal images, the thermal and RGB images that I selected as a subset. So I've got, let's see how many of these I have. 22 of them. And we're just going to do some stuff with it. Yeah. All right. So we're in here. And the first thing that we're going to want to do is import some things. And I'm going to import a lot of different tools kind of all at once. And I'm also going to import the utility functions that are in the merging utilities. I'm going to, in the merging utilities directory, I'm going to just go ahead and import all of those. So we're going to be using NumPy, and we're going to be using matplotlib. We're going to be using Seaborn, because it can be kind of nice. It's nice for some histograms we're going to write. And we're going to import some stuff from SciPy. We're going to import stats from SciPy. So there's going to be some other things. We're going to import some things from OS, and we're gonna do this in this main notebook. Although some of this might be a little redundant, and most of the lifting is going to be done from the Python files. So I'm going to import list directory and get current working directory. I'm going to get, let's see, I'm also going to import a bunch of stuff from skimage and some of their read and save functions. And then, let's see, skimage.color, we're going to need to be able to convert RGB to gray. And we're going to need some other functions as well. So let's go ahead and import those. So RGB to gray to convert RGB images to grayscale. HSV to RGB. And, you know, maybe I'll do this first. RGB to HSV. HSV is a color format, hue, saturation, and value. And we're going to be playing around with that. We're also going to do RGB to lab. Lab is a color format that essentially what you get out of it is the ability to have a consistent light value, and that's going to be helpful, as we'll see. So RGB to lab, and then lab to RGB, and these are just conversion functions. I should probably point you at skimage, so I'm just gonna do that. Okay, And what else do we need? Also from skimage, we're going to import image as ubyte. And that's, you know, just another, it's a formatting function that we're going to use somewhere. I'm going to suppress warnings. And hopefully we won't need to troubleshoot too much in the way of skimage stuff. There are different versions of skimage. So I'm just going to let that load up really quick. And then we'll talk about skimage. And I'm also going to import the utility functions from those VS Code documents that we just made. So those are, let's see, where are those? Thought I opened them. I must have closed it without realizing. So let me just open code. There we go. All right, so we've got imageutils.py, merging.py, osutils, and plotting.py. And we're just going to import all of those. We're going to be jumping around to all of these, so I'm just going to get them open in VS Code so that they're all here and I can switch between them really quickly. Plotting, osutils, merging py, and imageutils.py. Okay. So we'll get back over to here. And let me just get those names again. So that's from merging utilities dot image utils. I'm going to just import all of these functions kind of as they are. So I'll copy this. And so we've got image utils, we've got OS utils, we've got plotting, and we've got merging. All right, so let's see if all of that imports. RGB to gray. What is going on there? From skimage.color, I need to actually import. And let's find out if everything is going to work the way we expect. All right, while that's doing that, I'm not sure why that's taking so long to import, but let's go ahead and look over here. So scikit image, I mentioned this a couple weeks ago. Scikit image is a library that has a bunch of helpful functions for image processing. And so here let's just look at the RGB to HSV really quick. And you know, when we think about RGB, we're thinking about a red channel, a green channel, and a blue channel. Here we're thinking about a channel for the hue, or actually the hue here, and a value. And there's also the saturation channel. So the value is a multiplier on the hue and the saturation that will compose an RGB image. So that's another way to represent and view images that can be very, very helpful. And you know, one of the reasons for this, as we can see here, is that you can actually threshold an image, and this threshold here is based on a hue. So it's cutting out all values in the image that are below a certain hue. And this is a hue thresholded image. Here's a hue and value thresholded image. It doesn't appear that much differently. But one of the nice things about scikit image, so we've got all this code, just like with scikit-learn, we've got all this code. You can grab it, run it, and you know, they also have they have it in the form of Jupyter notebooks that you can just pull down and use. So let's check this. Doesn't look like there are any errors, thankfully. and we're going to go ahead and start coding some of this. Okay, so the first thing that we're going to want to do, actually, let me just sync this up. So git adder, and just add the imports that we're going to use. And here we're going to say, let's just read in the data. Oh. There we go. And so I'm going to get the current directory, and I'm just going to use get cwd. I'm going to get, I'm going to pull from the data directory, and that's going to be the current directory plus, well, let's just take a look at what I called that, images. So this is going to be slash images slash, well, I think it's just slash images, isn't it? Yep. Okay. All right. So slash images, and so we can do that. And oh, get CWD is not defined. Oh, it's without the underscore. Okay. And let's look at that data directory. So that is indeed where our images are located. So what I might do here, though, is I might write another function. And let's see. So I might write another function, and let me just take a look at this. Is that what I want to do? Yeah, I might write a function called getImageSets. And essentially what I'm doing here is you know, trying to get the Actually, do I even need to do that? Sorry, let me double think this for a second. So we've got the data directory, and we're going to want to pull these images. So let's just consider this. Yeah, I'm going to just write a couple functions here. So let's get the image directory, and this is going to be a relative directory. And let's say that this is just going to be images. And this the purpose of this is to allow it to be used by a separate script, which we're not going to do, but it's going to be helpful. So let's say there's a canonical directory, and that's going to be get cwd plus that relative directory. And we're just going to return the canonical directory. So why don't we, so we're going to need something here. We're going to need to from os import get cwd. So let's go ahead and use that over here. And we'll just go ahead and get from our data directory this let's make sure that this works properly. So that was from OS, and it's the get image directory. Not sure what my error is there. Oh, nowhere. So get image directory. Ah, I see the error. Okay. And why don't we go ahead and run that. And let's make sure that that gives us the same results. Get image directory is not defined. Of course it's not, because I need to run all cells above in order to have that work. And there we go. So that's the location in this instance. And so that should work on another computer. It should work in a script. You can get this get image directory, use this in such a way from another script if you have a different working directory from the Jupyter Notebook. So we're going to write another quick script here, a quick function, and that's going to be the get subdirectories. So actually, we're going to write get image sets. So why don't we go ahead and look at that. So I'm going to write def get image sets, and we're going to pass in a canonical directory, and that's going to be get image directory. And so let's also print the subdirectories, and I'm going to set that to false. And the reason I'm doing this is there are two subdirectories in the Kaist data, right? It's there's a thermal and an RGB subdirectory. So I'm going to just write directories are going to get the name from the name in listdir. So I'm going to need that. I'm going to import that. And that's going to be listdir of the canonical directory. If is dir, which we're also going to need. So join of the canonical directory, and then the name. All right, so let me just make sure I'm importing is directory. And that's just checking to see if something is a directory, right? I'm also going to need join. So from os import, let's see, is there anything else in here I need? Actually, from os import get cwd listdir, and we're also potentially going to want to make directories in a little bit. So from os.path, that's where I'm going to import isdir and join, and let's go ahead and import exists, and that's just to check if a path exists. All right. So from there, so we're getting the image sets. Let's go ahead and write some more logic here. And this is all just getting into the reading in of images, right? I'm overcomplicating this a little bit, but it's to make something that can be used in a scriptable way for a massive amount of images. So if print subdirectories is true, then let's just print the subdirectories. And let's do that like this. And I'm going to make some space here, and we'll just do the directories. So this is going to print all the subdirectories. I'm going to make that an F string. And let's go ahead and so image set file names. we're going to go ahead and make a dictionary. And for every directory in the directories, we're going to make a file list. The canonical directory plus the directory. And that file list is going to be each file name in the file list. And these are going to be JPEG images. So if JPEG is in the file name, and then let's say image set file names subdirectory is going to get that file list. And then we're going to return the image set file names. Okay. So let's go ahead and see if that works. Do I have a get? Okay, that looks good. So let's go ahead and see if that works. And got this data directory. And we're just going to say the directories, say get image sets. And now let's just, let's print the data directory. And let's also print the subdirectories, and hopefully, let's see, subdirectories, and that should be deers. So let's find out. Okay. Name get image sets is not defined, of course, because I didn't run everything above. And that's one thing about this approach, is you kind of have to do that. Okay. All right. So the subdirectories. So notice this is all the color images, and then this is all the thermal images. Maybe I don't want to print all of that. Let's just print a list of the keys. So I'm going to do that. Okay. Oh. There we go. All right. So the subdirectories are color and thermal, as we can see. All right. So now, one thing we might want to notice here is that if we're processing any of this, we probably want to check to see if these directories are parallel. And so I'm going to do one. I'm going to make a checker for parallel, not parallel. But to start off with that, I'm going to write another function called get the image sets, and this is going to get all our images for us. So I'm going to just jump back over to here, and let's go ahead and write, or sorry, not get image sets, but oh, we already wrote get image sets. I need to write a verify parallel file names, and so I'm going to do that. So the first thing I'm going to do here is, let's just see. All right, so image set file names, get image sets. And in this case, we're just going to use this directly. So I'm kind of using this twice. There's some redundancy here, but image set file names. And then I'm going to want to get the color image file names. And that's going to be image set file names sub color, right? And notice that's just the name of the directory. And then I'm going to get the thermal here. So thermal, and let's do thermal image file names. And let's check if they're parallel. All right, so we're going to write a verify parallel file names. So let me just do this. And this is going to be pretty straightforward function. So we're going to verify parallel file names, and we're going to pass in an image set, right? That's that dictionary that has color and thermal. And we're going to, we really want to see that we have the same sets of images. So the directories, I'm just going to make another variable here. And I'm going to make something called not parallel, just a list. And parallel is also going to be a list. And this is kind of a brute force approach, but it's going to work. So directories is a dictionary. I'm going to say for directory 1 in directories.keys. And then for directory 2 in directories.keys. If directory 1 is the same as directory 2, then continue. And I'm going to go ahead and code something that tells us what we're missing. So if dir1, actually, if directories underscore dir1 is not equal to directories sub dir2, then we'll ask if dir1 dir2 is not in not parallel, and dir2 dir1 not in not parallel, then let's just print a warning. And we'll just say warning, and these two directories are not parallel. And let's see. I'm just gonna use .format here, I think. It'll just be a little nicer. So .format and dir1, dir2. I'll use an f string. No reason not to. dir1 and dir2. And then, so there's our print statement. And again, this is just verification that we've got parallel RGB and thermal. So let's do not parallel dot append, and we're just going to append this to the list of not parallel in that event. And so, you know, that's if there's a nested if. Now, if they are equal, then we're going to do something else. And this is a sort of redundant form of coding that you might find yourself doing in cases where you're really trying to just verify something. And the reasoning for us doing this here is that we want to make something that will apply to the entire Kaist dataset and not just into this little tiny subset. So if dir1, dir2 not in parallel, and dir2, dir1 are not in parallel, right? Because we're doing all these comparisons. Then we're going to say print, and let's just do yay. And let's say, and both these directories are parallel. And that's just going to be, again, dir1 and dir2. Okay. And the next thing that we want to do is, we need to append those to parallel. So parallel.append, and we'll append dir 1 in dir 2. Okay, so once all of that wraps up, we want to return parallel, not parallel. And this just gives us the ability to check to see what we're missing in our, what may or may not be parallel. So I'm just going to write here, I'm going to write parallel, and that's going to get, so parallel not parallel is going to get that verify parallel file names. And we have to run everything above, so run all above. And let's see if this works. Oh, verify parallel file names, missing one required positional argument. Image set, which makes sense. So let's pass in the image set file names. And it turns out those are parallel, which is great. All right. So I think that's all of the sort of terminal work kind of stuff that we're going to do. Maybe I can make this a little bit bigger. Now let's go ahead and start reading in and looking at images. So I'm going to get a sample image. And let's look at these image numbers really quick and make sure that we're reading in a way that makes good sense. So got this, got color. Okay, so we've got 10, 72, 233. Why don't we just start with 10? I think that's a nice thing. So this is the image number, and that's going to be 10. Actually, yeah, that'll work. Actually, let's do 0 because it's the 0th image. Let's just do that. And we're gonna go ahead and I'm just gonna make something called image1 underscore RGB. This is just gonna be the image, the RGB image. I'm gonna use imread, right, which is from skimage. So from skimage, import imread. And we're going to get the image directory plus color plus the color image file name and sub image num. And this is just so we can, because we're going to pull in parallel images. This is just so we can pull something in really quickly. So I'm going to go ahead and do this again, except for the thermal. So color, instead of color, we're going to do thermal, and instead of color image file names, this is going to be let's see, is that what I want? This is going to be thermal image file names. Oh, no, color image file names. Yeah, I think actually. Oh, let's just see. And we're going to plot these, and this is going to be image1 underscore RGB, color image file names, sub image num plus RGB. And this parameter right here, or this argument I'm passing in, is going to be displayed above the image. So we'll see that in just a second. And this is comparative, so this is going to be a comparative plot. So image1 therm is going to be the other image we pass in, and it's going to be color image, file names, sub image, num plus thermal. And I'm just going to put an extra space there, make it a little nicer. So this function doesn't exist yet, and we're going to write it right now. So this is going to be in plotting. And for plotting, we're going to need a few things. We're going to need matplotlib, import matplotlib, .pyplot as plt. Again, we're going to use Seaborn. And you know what I'm going to do? I'm just going to grab these from here. We're not going to need everything here, but we are going to need some of these things. So I'm just going to paste all these in and delete what we don't need. All right, so we're going to need from skimage. We're not going to need any of that. We're not going to need anything from OS. We're not going to need SciPy stats. We do want NumPy. We want matplotlib. We want Seaborn. From skimage color, we want RGB to gray. And we might import some stuff from the merging utilities, but we'll worry about that in a little bit. Okay. So we've got what we need from there, and we're going to write a couple functions, right? We're going to plot images, right? And that's going to be comparative. But to do that, we're actually going to write a function first called plot image, and that's going to, well, actually, let's just write this plot images function. I was going to split them out, but I think this makes sense. So let's plot the images, and we're going to plot an RGB name, and then a therm and a therm name. So these are the images we're going to plot, and we'll start by creating a figure. And it's going to be 2 axes, and calling this with plt.subplots. And probably at some point I'm going to dig more into the basics of plotting. In this case, what my goal is to get us through some code that will allow us to visualize something. So this is just, you can take this for granted for now. We're just creating a figure object, and there are 2 axes. That's where the images are going to show up. So for axis 1, we're going to show that RGB image, and CMap gray gives us that image in a basic color scheme that we would understand. So we're going to set a title for this, and that's going to be RGB name, and we're going to turn off the axes. So I can take this whole snippet and I can do the same thing for axis 2, showing the thermal image. So axis 2, and I named that therm, and axis 2 set title, and that's just going to be the therm name. And axis 2 is off. All right. And I think that should just work. So let's go ahead and try that out. All right. So again, I'm going to run all the cells above, and let's see if this works. It does. So we've got a plot of these 2 images next to each other. And this is kind of nice because we've got this car hood over here, which I think is kind of indicative of heat from an engine. And here's a person. And the door here is warmer than things around it. You know, there's just some cool stuff going on, some lights and all that. So that's a good place to start. And, the next thing we might do, so this is, I'm just going to put a little statement here about plotting images. Escape, and let's do plot an image. And let's call this plot images. And here, the next thing we're going to do is look at RGB, look at the histograms for the RGB and the RGB channels and a grayscale channel. And I covered how to do this in the last stream with cat images. So I'm going to actually just copy some code from that, and I'm going to paste it in as one of our utilities. And I'll walk through it really quick, just as a refresher, but I'm not going to type all of it out. So let's plot some histograms. And we'll do that momentarily. All right, so to do this, I'm just going to grab, yeah, let's do this. All right. So I have this function here called plot histograms. So let's just go through this. Gray gets RGB to gray, and that's just up here, right? That's from SK image, and that gives us a grayscale image. Gray is going to get 255 times gray, and that's just to bring it back into scale. So it's a NumPy array, and it's going to be scaled from 0 to 1 in this RGB to gray, but we actually want it in between 0 and 255. And then I'm converting it to integer right here. So I could have done that up here, but I'm just doing it in a separate operation. Now, we wrote this last time, this averaged image. And this is going to be an average of, actually not last time, but 2 weeks ago, in the cat histograms stream. This averaged image is like grayscale, but it's a little bit different. Grayscale has, it balances it gives different weights to RGB. It doesn't give you an even, it doesn't give you the average, the actual average of this channel plus this channel plus this channel divided by 3. So we're going to write another function called averaged image, and that's going to be one of our first image utils. So the first thing we're going to do is, well, we're going to write 2 functions actually, and those are going to come from this merging utilities, which is essentially from our image utilities, and it's going to be average image and split layers to 3. Split layers to 3 is going to give us our red, green, and blue channels, which we're going to use. So why don't we, I could just write that first. Yeah, why don't I write that? So averaged image is going to get the average image of the input image, right? And so let's go over to image utils and let's write a function. So yeah, let's write average image, and that's going to take an image, and there are going to be 3 layers: layer 1, layer 2, layer 3. Now I could have called these RGB, but there's a reason I'm not. I'm not calling this RGB because we could average any kind of 3-layered image with this, and I actually want to, use this on an RGB image, so that's fine. We could call it RGB, but I want to make this a little more general, so I'm just calling it layer 1, layer 2, layer 3. And we're going to split the layers of this input image. So we're going to split this to 3, and that necessitates us writing another function. So this is going to be split layers to 3. And let's just return. So it's going to be, we're going to return everything in the channel being the specific frame, right? The R frame, G frame, B frame for channel in range. And we're going to sort of hard assume here that there are only three channels in these images, that there's not a fourth alpha layer or something like that. And so now that looks like it should work. So that's just going to give us these 3 channels, layer 1, layer 2, layer 3. And we're going to average these. I'm going to say averaged is going to get, there's 3 of them. So I'm just going to hard code this. So I'm going to say 1/3 times layer 1 plus 1/3 times layer 2 plus 1/3 times layer 3. So I just need to change these. So layer 2 and layer 3. And we can just return this. So let's return the averaged as type integer. So we're changing the type of this in this case. And that's because these layers are going to be filled with float values, and we don't actually care for them to be floats. It's okay if they're floats, but it makes more sense if it's between 0 and 255. 0 being black, 255 being white, let's say, or 0 being no luminosity, 255 being full luminosity of that layer. Then really int is the type that we would expect, unless we were using 0 to 1. So let's see, make sure this is how we'd expect this. Yeah, let's do that. I think that looks good. All right, so from there, we were writing a plotting function. Yes. So we're plotting histograms. The averaged image is going to get average image of the image, RGB, split layers to 3. So these are going to be RGB. Now notice here, if we're showing the images, then we want to show the grayscale luminance, which is that RGB to gray. And then we're going to plot the image, and we're going to plot the histogram. We don't have a plot image or plot histogram function yet. So why don't we write those? So this is plotting histograms. I'm going to write a quick plot image function, and then I'm going to paste in a plot histograms function. So okay, so I might as well write this plot images is here, but why don't we say we have plot image as well. So we're going to plot an image with its title, and kind of in this same vein, we're going to do plt.subplots and the number of columns. We want to be able to use this independently of our other functions. So I'm just going to do it like this. So sharex is true, and let's also do share y. Share y is true as well. Okay. And what's next? Oh, yeah, we just want to show the image. And we can use skimages IMShow for this. Actually, this is PLTs, not skimage. So cmap gray, and let's set the title. So this looks a lot like our function below, and we're going to turn off the axis. So ax1.axis, and that's going to be off. Okay, so that's plotting our image. And then the next thing, so we've got plot image, and then we've got plot histogram. So the reason I have images true or images false here is that we could plot the histograms without plotting the images. And the histograms here are, very telling, but this is going to give us the images and histograms together. And I think that's a really good thing to see. So this is a fairly involved function, and I wrote it previous. So I'm just going to paste it in here, and we'll take a look at it. All right. So I think not seeing any errors in there. All right. So with the histogram, we're setting up the subplots. We're calculating the standard deviation across the channel, right? That channel being red, green, or blue, or grayscale, or average. We're getting the mean, right? So this is a fairly common thing that you're going to want to get from an image channel. You're going to want to know the mean value. You're going to want to know the standard deviation. And that's going to be very telling of the image as you look at it. We're also, so this is just unwinding that matrix into a long vector, and we're getting the minimum and the maximum value and the range. We're setting a number of bins for the histogram, and we're assuming 255, right? And 255 colors, and then we are going to limit the bins to the range divided by 3.5. Okay, so we'll see that in just a moment. And then we're going to fit a line. That's just kind of nice to see a visualization of the line. And we're going to show the actual rates in the rates of certain values, certain pixel values. And we're just calling that probability density here. So we're going to display the mean, the standard deviation, and also the title of the image, right? So we've got the title of the image, the mean, the standard deviation, and then we're just making it look a little nicer with both this dark grid and a distribution plot with 75 bins in this case. So this is gonna be kind of nice. And there's also some code here so that we can save out this visualization. So let's go ahead and plot those histograms and see what we get. So I'm gonna write plot histograms. So that's image1 underscore RGB. You know what? I am really sorry. Let me just go ahead and sync this up. So plot histograms. That way, if you're trying to run this, it'd be kind of impossible to read through my added snippet of code without taking a look at the GitHub repo. So we're going to plot the image histograms for image1 RGB. And the title for that is going to be the color image file names underscore the image num, right? And this is nice because we can just change this image number and just grab that anytime. And let's say plus RGB and images is true. Nope, images is true. Okay. So this is just going to be for this one image. Let me just double check my function over here. Plot histogram. Yeah, so image, title, image is false. Great. Okay, yep, we're good. And again, I have to run everything above so that we're importing these new changes. And I'll go ahead and run this, and let's see if this fails terribly or does what it's supposed to do. And it actually looks like it did what it's supposed to do. So here's our grayscale image, and this is still running. And here's our luminosity histogram for that. And you can see we've got a shape here where we've got a lot of this sort of darker gray, you know, this sort of muddy gray. And then we've got some really washed out values at 255. And that kind of makes sense, right? So this is the weighted channel. Notice we've got, on average, the luminosity is at 160 with a standard deviation of 47. And if we look at this, that makes some sense, right? Oh, whoops. I didn't turn the grid off on one of these. So here's the average channels. And, oops. So the average channels are going to look a little bit different. And notice in our average histogram, it's 155 and 46, which is not that different from 159 and 47. So let me just, okay, well, you know what? We'll just go with it. So in our original image, right here, we've got some reds. There are some red values, right? Some red contribution. And so we might expect to see some contribution of that, right? So here's our reds, here's our blues, and here's our greens. And it's interesting, I think this is a facet of it being at night. It's interesting because these histograms don't look that different from each other, right? And there's a reason why we've got this sort of like bump on the right with both with all of these. It's that we've got things washed out, and if they're washed out like this, that tends to mean that there's 255, 255, 255 in the red, green, and blue channels, and if you have that, these are going to be completely washed out white, right? So that makes a lot of sense. Now that's going to be for our RGB channel. And you might wonder what's going to happen if we do the same thing for the thermal image, right? And yeah, so why don't we see? It's going to be, you know what? Let me fix this. I think there's something I'm missing in terms of turning off. Let's see, Ax1 axis. The axis is off here. Oh, I'll have to track that down at some point. Why we're sort of missing these, why some of these images are showing up with the axes. So it looks like I'm turning that off, but I must be missing something. Okay, I'll troubleshoot that later, and I'll update it in the GitHub repo. Okay, so let's plot the histograms for image1 _ thermal. And we can use that same file name, like the file names are purely parallel, and we can just do image num, and then we can do, let's just do that, therm, and images, let's show all the images. Okay, so here we've got the thermal image, and that grid is a little annoying, but we'll live with it. So the luminosity histogram here is, I mean, this makes a lot of sense, right? We have very little in the way of high values, and we do have some things that look like they could be washed out, but they're probably a little bit gray, actually. And all of these plots are really going to look almost exactly the same. And this is an interesting thing about this data set. The thermal images have 3 layers. They actually have, you know, I'm saying red's histogram here, but that thermal camera has 3 layers. And those layers happen to be nearly identical, but they're not identical. Like 52.011 Oh, well, that is a bad example. Reds and blues here are identical. But notice the greens is a little bit different. And, you know, ultimately these are almost exactly the same, but they're slightly different. They are slightly different. And so, you know, you may think to yourself, well, would it make sense given that this thermal, because it seems like you'd only need a single layer for a thermal image. But given that these thermal images are 3-layered and those layers are slightly different, maybe it makes sense to average all of those down to a single layer in the case of analyzing these. Not going to worry about that too much, but it's something that you might want to consider. Okay. All right. So that's our, you know, that's a look at the thermal histograms. And probably what we'll do actually with these the thermal layers is we'll just pick one and use it. So yeah, or we'll average them. We'll find out. All right, so let's start thinking about things we can do to pre-process these images. We're going to fuse these images in some way. So I'm just going to make a section here called merging images. And let's first take sort of a naive approach and let's average each layer with the thermal layer. So if you imagine what we're doing here, if we're taking this original image, actually I'm going to go ahead and comment these out for all these histograms, so that we're not running this over and over again when we run everything above. If we're going to average the red channel against this thermal, we're going to be sort of incorporating information from the thermal image into the reds channel and the blues channel and the greens channel. And we're going to maybe lose a little bit, but we may gain some prominence for things that are warmer, right? We're going to be kind of suppressing. We're almost using this as an average mask of some kind. We're kind of suppressing the color that we see that is only a reflection of light. Notice here, we've got this, this curb, or this step. I guess that's a bottom step. That bottom step is very brightly colored in the image, but it's not emitting any heat. So we might punish that a little bit by averaging it against this really dark color. So why don't we go ahead and think about how we do that. All right, so I'm gonna just repeat some things here. So the data directory, I'm gonna get the image directory, and we'll go ahead and use that same sample number. Let's say sample number is 0. And let's get the image 2 RGB and image 2 therm. Image 2 RGB, we're just going to read in the data directory plus color and color slash actually. Oh, let me go ahead and push all this code. I'm just going to say update. Sorry about my my GitHub commits. They're not ideal, but I don't want to spend a lot of time writing commits, so I'm doing this kind of on the fly. So I am read, let's see, color plus the color image file names sub the sample number. So I'm just grabbing the sample number out of our list of names. And I just do this. And is that what we want to do? So our thermal image, IMRead, the data directory. Oh, sorry. We just need to change this to thermal. Yep. Okay. All right. So we're going to average each layer with thermal layer. And to do that, we're going to write a function. And I'm going to call out to average layers with thermal. And this is going to be image 2 RGB and image 2 therm. So you might be saying, well, do we need to write this function? And yes, we do. So why don't we go do that? So let me just go over here. And this is going to be under our merging. And let's see, what is this average layers with thermal? Okay, so we're gonna need to import some stuff, NumPy. Again, I'll just grab these from the top of this Python notebook. And I'm not sure everything we need out of there, but let's just grab it all and reduce down to what we need. So we definitely need NumPy. We don't need Matplotlib or Seaborn. We don't need SciPy stats. We don't need OS. We don't need IMRead and IMSave. But from color, we do need RGB to gray. HSV we're going to need eventually. RGB to HSV, RGB to lab to, yep, we need all those. We do need images UByte, and we don't need this import warnings. And we're going to import from image utils. And we're going to import from OS utils. That looks right to me. Okay. So what is the name of that function we're writing? It is, go back down here, average layers with thermal. Great. So let us average some layers with thermal. Okay. All right, let's call this average. Shoot, sorry. Need to go back and check that name again. Let me just copy it. It's the thing about names. You kind of constantly have to be remembering or not, and remembering is hard. So let's pass in an RGB image and a thermal image, and we're going to split into the RGB vals and yeah, vals, and let's say RGB, and we've got that split layers 2, 3, RGB. Let's go ahead and look at image utils. Okay, average image and split layers to 3. Great. And back over to here, average layers with thermal. Split layers to 3 of the RGB and average therm. So we're going to take that thermal image and we're just actually going to call out to that average image function we wrote earlier. And we're going to take those 3 thermal layers because there's some slight variation in them. Instead of just dropping 2 of them, why don't we just average them all together? We already have the function. So let's do that. And then let's create an empty array and populate that. Populate for the new image. All right. So RGB array, and I'm going to just fill it with zeros. And that's going to be based on the shape of the RGB image. And remember, these images are parallel. The RGB and the thermal images have the same shape. And so we're just gonna say RGB array, and we're gonna fill this with averaged values between R and the average therm, G and the average therm, and B of the average therm. So we're gonna have to write another function, and that's gonna be this average, the matrix. And let's go ahead. I'm just gonna do these really quick for the 3 layers. So everything channel 0, channel 1, and channel 2. And then we're gonna, you know, we're just filling in these channels. So this is gonna be just R, G, and B on the average therm. So we just need to write this average matrix function over here under image utilities. So def average matrix, and let's see, what's the best way to think about this? It's just going to be half and half, you know, so it's just going to be matrix 1, matrix 2. And this is one of those functions that, you know, we probably could have just done it in place with the other function, but perhaps there's an opportunity to use this somewhere else. I don't think in this project that'll be the case, but it's nice to kind of see functions atomized. So this is generally how I write my syntax, but this is more Pythonic, so maybe I'll just do that. Okay. Oh, but then I have to fix it there. You know what? I'm just gonna do it my way, and it'll be fine. So half of matrix 1 and half of matrix 2. In this case, this could be the R and the thermal, the green and the thermal, the blue and the thermal. And it's just going to take half and half and return all of those. So I think that, okay. So that's not seeing any errors, nothing outstanding. And all we need to do is return this. And let's find out if this does what we might expect it to do. So this is averaging each layer with the thermal image. Let's jump back over to the Jupyter Notebook. So, so we're calling out to that function. Why don't we go ahead and run everything above and make sure there are no errors as yet. So we're just waiting for those to run. And we don't actually need to plot that anymore. So let me just get rid of that. And then if we run this, we don't get any errors yet. I'm going to assume that it's working, but we're going to find out. So let's plot, we're just going to plot images of this averaged image. So plot images of image 2, RGB, the color image, file names, sample num, right? That's just the, you know, I should just be copying these. It's okay. Oh, there it is. Color images, file name, sample num. There we go. And that's going to be our RGB channel. And then we're going to compare this. Well, yeah, we're going to just look at both of these. So this is just to have everything in one space. And that same, we're going to compare that to the thermal next to each other. So these are the original images. And then we're going to plot the averaged image 2. And that's going to have the same file name, right? And let's just make a note here, RGB averaged with thermal. And let's take a look. Course name average image 2. Averaged. Let's see. Oh, just name it average image 2, not averaged image 2. That's fine. Okay. So notice there are going to be some values that are out of range. And, oh, actually, that is failing for some reason. So this is where we troubleshoot. I may not have saved it. So let's run it all again and see if this works now. Nope, same error. All right, let's track this down. Okay. Split layers to 3. Average therm gets average image. MP zeros, RGB shape 0, 1, 3, 0, 1, 2, RGB, average therm. So maybe what's happening here is with average therm. Okay, so average mat 1, mat 2, 1 for 2, matrix 1, matrix 2. Huh. Yeah, I'm not seeing the error here. Yeah, let's try that again. There we go. We're actually getting something out of this now. Okay, so, you know, let me just double check this this plot images function or plot image function, because we are getting these grids and we do not want them. They kind of get in the way. So let's just double check that. So plot image, x1 axis off. Oh, that is why. Okay. All right. So we're well on our way now, now that that little bit of troubleshooting's gone. Now we can look at this sort of image fusion, right? And we can think of this as a pre-processing technique where, you know, we've got these parallel images, but you could imagine we could have completely disparate images as long as they're the same size, and we could take an averaged version of one image, like a grayscale image, and use it as the color base, as an averaging color base for another image. So why don't we take a look at this more closely. I'm just gonna snap it and make it a bit bigger. And with this, anything that has a thermal presence in the thermal image has been brightened, and everything else has been darkened just a little bit. One thing you might notice, there's a little bit of glow around this person, and you can see a little glow off to the side, and that is the offset. That is the because those two cameras for the RGB and thermal images, because those were a little bit distant from each other, and because probably their angle is a little bit different, we're getting a difference in how we're seeing this. So that's kind of interesting. And yeah, we're just seeing something a little bit offset there. Okay. So that's cool. But let's do some other stuff. Let's think about, well, so we could compare the histograms of these, but I'm not going to. I'm going to go ahead and skip that part of it. But if you wanted to, you could also look at the histograms. But, you know, that's just, again, plot histograms, and you can throw this image in there on your own. So let me go ahead and sync this. So this is averaged therm with RGB. So that exists. All right. So let's think of another approach here. Let's threshold by a certain level of thermal luminance. And this is going to be slightly more involved. Well, I don't want to take up too much time. I kind of want to do the coolest thing. I'm just going to skip to the coolest thing that I want to show you. So, and I'll go ahead and sync up everything else that I think is interesting, and you can go over that on your own time. But the thing I really want to show that was part of just I don't want to say it was a discovery, but it was something that I think I came up with. I'm sure somebody else has done it, but there's a color space called LAB, and what I chose to do was replace a sort of standardized set of light, a standardized measurement of light in a converted image in the LAB space. So we've got RGB. LAB is another representation of color. So there's a lightness layer, and that's the L in LAB. So LAB has a standard illuminant that you give to it, and with that, you can get a sort of scalar value for each pixel's light. And I just took that away from the RGB image and replaced it with the thermal. And it gives a very... it's something that if I was Predator, it's the way that I would want to see if I was Predator. You know, not this pure thermal vision, but this type of vision that is a combination of RGB and thermal. And yeah, it's kind of beautiful also. It makes me want to create thermal imaging as a, like, you know, I want to go out and film with parallel cameras, all kinds of stuff and do it. So I'm going to stop talking about it. I'm just going to do it. So let's convert RGB to, so we're going to do this in stages. We're going to convert RGB to LAB. We're going to replace the L with the thermal, and we're going to revert to RGB when we're done. If you're familiar with HSV, LAB is sort of similar to HSV, but the value is not, so L is not a multiplier on the other color values, the other channels. L is a value that sort of stands alone. You can look at it as a pure luminance. Okay. You know, little side story. It serves to address perceptual uniformity property, and that kind of ensures the difference between two colors as perceived by the human eye. So LAB color kind of has the distances should be proportional to the Euclidean distance within the color space. So it preserves that distance in RGB, whereas HSV does not. So we're going to go ahead and go for this, and let's see how it turns out. I think it'll be cool. So samp, let's do samp 3. And let's do that first image again. And let's do image 3 RGB. We're going to do image 3 thermal. And I can just snag this from up here. And I'll change some stuff around. Actually, I'll snag all of this. And then we'll get into writing the function. Just save some time. So this is going to be samp number 0 image. Let's just image 3. Image 3. Image, average image 3, except it's not going to be average image. It's going to be, let's call this image 3 luminance with thermal. And we're going to write a function called replace the lightness with therm. And that's going to be image 3 RGB and image 3 therm. And then when we plot the images, I want to just grab these image 3 RGB. It's going to be image 3 luminance with therm. Change this is going to be luminosity replace with thermal. And what else? Image 2 therm, RGB thermal, image 3 luminance, image 3 RGB, image 3 therm. Okay. So we need to write this function, this replace lightness with therm function. And yeah, and I don't know. I think this is going to be cool. It's going to turn out well. So let's jump over to here, and I'm going to put this in the merging.py. So average layers with thermal, we wrote that. Let's write whatever I named it, replace lightness with thermal. Okay. All right, so let's call this def replace light with therm. Did I do light or lightness? Oh, appears I called it lightness. Okay. I'll just call it light. Why not? And okay, so replace light with therm. We're going to pass in the RGB image, the thermal image, and we have to create an illuminant value. And what I found with this is that, and you can read up on lab to understand more about this, but this is sort of a standard illuminant D65. So I'm going to go with that, and I'm just going to make a note of some other illuminants. Let's say, you know, choose from these because these are going to make sense. And we'll do A, D50, D55, ooh, not 44, but not, yeah, D55, D65, D75, and E. So all of these will give you slightly different results, but they all kind of make sense. And so I'm just including them in there if you want to play around with it. So let's split the RGB values. And so note that if there is an alpha layer, which is a sort of transparency layer, this is going to drop that. So let's first convert to the lab space, RGB to lab. So this is RGB, and let's pass in that illuminant. Okay. And what else? So average, we're going to average the thermal image again. Just kind of makes sense to do that. And then we're going to create 3 channels, LAB, and we're going to split the layers to 3. And you might notice that this is looking really similar to this prior function. And, you know, it's going to continue to look similar. But we're going to do something a little bit differently. So lab has a different range. And that the L in lab is ranged from 0 to 100. So we're going to change the range of the thermal image. We're going to scale it to between 0 and 100 in order to make a proper replacement so that we can replace the L layer, the lightness layer, with values that make sense from the thermal layer. And then we're going to convert back to RGB at the end of this. So let's set the range to fit in the LEB L range, which is 0 to 100. And we're going to scale that thermal image. So average thermal scaled, it's going to be, I'm just going to interpolate the average thermal and the min of that against the max of that. So the min value and the max value. And that's going to end up being scaled from 0 to 100. 0 to 100. Now I could scale it to something else, right? I could scale it to 0 to 1000 or something like that, but 0 to 100 is the range for lab, the L layer in lab. So that's what I'm going to do. And then just like we did before, you know, I'm actually going to grab this snippet of code. I'm going to create an empty array and populate it for the new image. And this is going to be very similar. So I'm just going to grab this whole snippet from the prior function. And let's go ahead and throw this in here. And instead of RGB array, I'm just going to call this new LEB. And I'm going to copy this across. This is the thing about learning your workflows. You know, you're going to do a lot of copying. And that's good. Okay, so the new lab is going to, this is an empty array, numpy array. So np.zeros, all the default values are 0. RGB shape 0 is the same shape as our RGB image. So new lab, and we'll just change this a little bit. So this is just saying the whole thing. It's just a different notation to do the same thing. But I prefer this notation, actually, even though I used a different notation in the prior one. So let's do that. And we're going to call out to, so the new lab, this layer, this is the lightness layer. Oh, let me change that to 1 and that to 2. This lightness layer, layer 0, is actually just going to be, it's just going to receive the average therm scaled that we just made. And that's all that's going to do. And then these other two layers are just going to receive the A and the B layers that we split out before. So what we've essentially done is we've thrown away the lightness of this image and we've replaced it with the thermal. And if everything worked, if everything is as we expected, this should work. So let's find out. And think I'm missing anything here. Nope, I think this is what we want to do. So cell, run all above, and oh, I could have just commented these out. Let me just comment those out just to have them not running. So let's run all above, and let's run this. And let's see what we get. Ooh, that is not exactly what I expected. What is going on there? Let's just take a look. So, oh, I see. Okay. So I didn't convert it back to RGB. And, you know, it's hard to get a read on this in light of this. I'm not sure how to interpret this this lab image, except that it's, you know, it's a bunch of noise. So we actually need to convert this back. And that's easy enough to do. We imported this function before from skimage, so new RGB. This is just going to get lab to RGB. So I'm just making the conversion here. And I'm going to convert new lab. New lab. And I'm going to return the new RGB, but I'm going to also convert it to bytes. So, oop. Oh geez, what did I do? There we go. I hit a wrong button. All right, I just changed the scale of the view. So I'm going to return new RGB, and these should be bytes. These should be, this is just changing it to bytes. So let's see how that goes. I think it'll be cool. And let's go ahead and run it. Find out if it works. Ooh, well, that's not a good sign. All right, what is happening? You know what? Let me try this with a different image. I think there's something wrong with the function, but yeah, definitely something wrong. All right, so let's look at that original image, and let's jump back over to here and scan through and see if there's something going on. All right, so I bet there's something wrong with the scaling. So interpolation, average therm min, average therm max, 0 to 100, no? That looks right. Split layers to 3. Image lab, RGB to lab, RGB illuminate. You know what? Let me just make sure. No, that looks right. Okay. Average thermal gets average image, thermal, LEB, split layers to 3, scaling it, average therm min, average therm max, 0 to 100, that looks correct. NP zeros, that looks correct. Oh, you know what? I bet that's it. It's because I copy and pasted code from up here. And I think at this point, yeah, at this point, our values are slightly different. So let's see if that works. All right. Oh yeah, awesome. Okay. So here's our RGB original, here's our thermal original. But let's take a look at this luminosity replaced with thermal. And it's a little misleading to say luminosity replaced with thermal, because it's sort of that, it's not exactly that. But notice we're preserving some color state, and we're preserving the sort of morphology of the image. Like you can see these steps, you can see these color contributions and whatnot, but you can definitely see heat coming through. And that's really, you can imagine that as being super helpful. You know, like, you could imagine a lot of different applications for something like this. Like, what if you had goggles that were, that had this simple function, this simple function that processed frame by frame what was coming in, this replacing the light with the thermal, and you were, let's say, you were hunting, or you were observing, let's say observing things in a forest, or you're looking at a factory floor and you're looking for machinery that's potentially overheating, right? This could give you a path toward a type of analysis that in real time, that would be really helpful. The way we were using this approach was pre-processing images as another image to pass into a neural network that had 3 inputs: one input for RGB, one for thermal, and one for this thermal RGB mixture, right? Where lightness is replaced by the thermal luminosity. So yeah, you can imagine a lot of situations where this would be helpful. Okay. So I'm going to go ahead and sync this up. So let's call this replace lightness with thermal. And I'm going to go ahead and drop some more code into this. I'm gonna stop here because I think, the point has been made, right? There are these approaches to image processing, and this might be a little bit novel, and maybe a little bit specific, but you could use 2 different images. They don't have to be these parallel kinds of images, and you could take the grayscale, the light of one image, and you could use it as a modifier on another image. And that might be artistic or something like that, but you can imagine with actually pure parallel images, there are a lot of opportunities for generating something that has a new kind of signal that might give you new intuitions as to some phenomenon you're observing. So yeah, that's me. My name's Tovio Roberts. Not sure yet what we're going to do next week, but it will probably be something a little further image related. And I'm going to add a few more things into this GitHub repo that you can play around with just for fun. And yeah, thanks so much for watching.